my final project is on energy performance estimation for buildings. The whole point of this final project is I'm working with a simulated data set that there's a published paper for, and there's a specific claim that they make in the publication that for this type of problem, but especially this data set in particular, classical regression modeling is insufficient because the relationships between variables are highly nonlinear. And so the whole point is to just address that claim. In the data set, there's 768 observations. Those are the buildings. There's 2 response variables and 8 predictor variables. And for all of the buildings, there's 12 forms and 18 elements, and there's a lot of constraints around how the data was simulated. Some of those constraints are all the buildings are in Athens, Greece, with 7 residents. They have a fixed activity rate. All of the internal and thermal properties are the same. And then when you combine different variations of forms, blazing area variation, distribution, orientation, ultimately you end up with your 768 buildings. And so, top right, I just have an intro plot, just make sure that that's clean, it looks good. And then in the bottom right, I have all of the variables that I'm using. So, like I said, there's 8 predictors and there's 2 response variables. And so, in this project, I'm creating 2 models, one to estimate heating load, one to estimate the cooling load, and then I'm going to compare the error metrics I'm using are mean average error, mean square error, and mean average error. In the original work, they report those for the models that they use, so then I get my own results using the same experiment that they used, and I compare my error metrics. So a brief background on some of the techniques that they used, and then a little bit on Spearman correlation. So in the original work, they used iteratively reweighted least-squares and random forests. And so briefly going over those, iteratively reweighted least-squares is you have a regression model where you're using all of your predictors in their case, and you're fine-tuning the coefficient values through some error metric. I think they use maximum log likelihood. And ultimately, the goal is to beat down or lower the coefficient values for bad predictors and then fine-tune the good predictors. And that's supposed to help model fit and your least squares error. And then they also use random forests, which was discussed a little earlier. Basically, you have your ensemble of trees. They have different subsets of the data, different predictors, and they are learning to make predictions of what your response variables should be. For regression, you end up with a prediction for your response variable. You aggregate everything, you take an average from all of your trees, and that's your estimate of the response variable. And then here I'm using Spearman rank correlation. We didn't go over that in class, but I'm using that because that's what they used. And they use it because a lot of the predictors have non-Gaussian distributions of nonlinear relationships. So that's why, in this case, Spearman rank correlation is preferable over Pearson. And you can interpret the coefficient values the same way, -1 to 1. So for EDA, I'm really just looking at the relationships. I'm looking at what kind of distributions I have. Are there any linear relationships? I already kind of knew from the paper there weren't going to be. So I start with the scatter plots. So in the top left, I have my 2 response variables. The rest are all my predictors. There's really only 2 linear relationships between the 2 predictors, which is not helpful because they are not, or 2 response variables, and they are not used as predictors of one another, so that's not very helpful. And then there's one other linear relationship between relative compactness and surface area, but otherwise, this data is very discrete. All the relationships are going to be nonlinear, and their claim is starting to look valid. For the predictor histograms, there's an array of distributions, so really here I'm just trying to get a sense for what the data looks like. We've got one normal distribution, a left skewed distribution, piecewise uniform, and discrete uniform. And then the responses, they look a lot less discrete. They are bimodal in nature, maybe slightly imbalanced, but this is the data set that we're working with. And I'm not using any transformations because they didn't, so I'm going to try to keep it as apples to apples as I can. For the Spearman rank correlation matrix, just looking at the values that we get out, the predictors that have the strongest relationships with the predictors are overall height, roof area, relative compactness, and surface area. Wall area has a moderately strong relationship with the predictors, but the rest have little to no relationship with the heating. Okay, so for my two models, my selection process for my MLR model, or models, I'm just using the selection processes that we learned in class. So I do forward selection, backward selection, stepwise, and best subset. How I pick my model is I'm looking at the adjusted R squared value and the root mean square error value, but I'm also considering how many predictors I'm using in the model. And so from all of the models, we essentially have the same adjusted R squared, the same root mean square error, and ultimately I'm just going to take the model that has the least amount of predictors. So for heating load, that ends up being 6 of the 8 predictors, and they're noted here. For cooling load, it's the same thing. It's using 5 of the same predictors as the heating load model, but we're not using glazing area distribution because it was found to be insignificant for the cooling load. Okay, so for analysis, the experiment they did in the original work was they did a 10-fold cross-validation procedure over 100 repetitions. I'm not going to go into depth on really how that's done, but it's basically just randomly splitting the data into different subsets, and then training on the training data, testing with your single test fold. You do that 10 times for 1 repetition. You do it 100 times, you end up with 1,000 error metrics. And so on the bottom left here, I have my MAE, MSE, MRE equations, and then over on the right for the heating load model here, I have the average reported value for each of the error metrics across 1,000 experiments, plus or minus the standard deviation. And so this is going to tell us if the claim that classical regression modeling is insufficient or not for this particular problem. And they're right. RF does significantly better than the MLR model and the IRLS model. What's interesting is the MLR model does a little bit better in MAE, a bit better in MSE and MRE than the IRLS model. For cooling load, it's kind of the same result, but there's a little nuance. So IRLS does better in regard to MAE, but MLR is doing better in MSE. So what it's telling us is that while the cooling load MLR model has, on average, higher errors, the fact that the MSE is lower is a good thing because it indicates that it has less extreme errors and it's less prone, less prone to those errors that will do better with handling outliers and new data. But ultimately, RF is the best model by far to use of these 3. And then here I look at the importance of variables. That's something that kind of can naturally come out of a random forest model. So the way that I'm doing that for the MLR model is all of my predictors are standardized, and then I can look at the magnitude of the coefficients. And so the larger the magnitude, the greater the effect on the predicted value of my response variable. And so in the parentheses over here, I'm kind of showing like 1 for glazing area of the RF model to tell me that's the most important variable for the RF model. And if you go through this table, you see there's some general agreement, but there's some variables that the MLR model significantly overvalued for its significance, like overall height. I think the MLR model got that second in both response variables, but it was totally insignificant in the RF model. So I have my final model interpretations over here. The way that we interpret these with the predicted variables, the standardized variables, is that if you use relative compactness, for example, with the heating load, for for every one standard deviation change relative to compactness, the expected change in heat load is 6.85 units when all the other variables constant. And to wrap it all up, this project focuses on replicating the experiment done in the original work and addressing the claim they made that classical regression analysis is insufficient for this data, and we found that it's true. Random forest is superior. I just want to note that it's not generalizable to the real world because it's simulated data. There are a lot of constraints on simulating that data, but it is a good approach for taking different models and seeing which ones perform best with the data sets. So